Hello, in this video we'll be taking a look at rectilinear motion, which is a very important application of the use of derivatives. So we'll be taking a look at two questions to explain this concept. So the first question we'll be looking at is this. We're told that a tennis ball bounces so that its initial speed straight upwards is b feet per second. Its height s in feet at time t seconds is given by s is equal to bt minus 16t squared. So we are required to find the velocity at time t, then we are also required to find the time at which the height of the ball is maximum. The third question here says we should find the maximum height. While the fourth question says that suppose that when the ball bounces, says that suppose that when the ball bounces the second time, it rises to half the height of the first bounce, then if the ball continues to bounce, we are required to find how long it takes before it stops. So this is a very interesting question. Let's take a look at it. Let's represent the initial speed as v naught. So we're told that its initial speed is b feet per second and its height is s, and s is given by bt minus 16t squared. we've been told this. So to find the velocity at time t, the velocity a is the change in displacement divided by the time. So the velocity at time t is going to be equal to ds dt. On differentiating this, we have b minus 32t. Therefore, if we represent velocity as v will be equal to b minus 32t. And that's the solution to the first question. For the second question, we are told to find the time at which the height of the ball is at its maximum. So for the ball to be at its maximum height, we are trying to find a stationary point, quote unquote. So if we are to evaluate this, we are trying to find the point at which the velocity of the body is zero. Because when you throw a ball upwards, it starts with an initial velocity that you give it with your hand or whatever you use to launch it upwards. So the velocity keeps reducing due to the resistance of the air or the environment that it is around. But as it gets to its maximum height, the velocity becomes zero, then it begins to drop. That's exactly what we are trying to do here. We are looking for the point where the velocity of the body is zero. At what time does that occur? Since we know v to be equal to b minus 32t, you can say that when v is equal to 0, we have b minus 32t to be equal to 0, b is equal to 32t, and t is equal to b divided by 32 in seconds. So this is the time at which the velocity of the ball becomes 0, and invariably the height of the ball is maximum. To find the maximum height, we can now substitute the time it takes for the ball to get to its maximum height into s. S is bt minus 16t squared, and we know that t is equal to b over 32 for the ball to be at its maximum height. Therefore, s is equal to b multiplied by b over 32 minus 16 multiplied by b divided by 32 raised to the power of 2. So s becomes b squared divided by 32 minus 16b squared divided by 32 squared, which is equal to b squared divided by 32 minus b squared divided by 64. Therefore, s is equal to b squared divided by 64 feet, and this is equivalent to the maximum height of the ball. So now the fourth question is a bit tricky, but it's very straightforward too. So suppose that when the ball bounces a second time, it rises to half of the height of the first bounce. And if the ball continues to bounce this way, how long does it take before it stops? Now let's bring this to a real life setting. If you have a ball and its initial height of bounce was say 128 feet, so it means by the time it goes up after the first bounce, it starts the second bounce. The maximum height it now gets to is half of 128 feet, which is 64 feet. On the third bounce, the maximum height becomes 32 feet. On the fourth bounce, it becomes 16 feet. On the fifth bounce, it becomes 8 feet. On the sixth, it becomes 4 feet. On the seventh, it becomes 2 feet. On the eighth, it becomes 1 feet. On the ninth, it goes on to become 0.5 feet. What you realize is that the height of the bounce of the ball, the maximum height at which or to which the ball will bounce will never get to zero. It will just get closer and closer to zero. It becomes very small, like infinitely small, but it will never become zero. So the best way to do it is to think of it as the ball stopping when it gets to infinity, because in reality the ball never truly stops. The only time it stops is okay, there is an external force applied, probably through the air resistance around it. That's when we can see the ball stopping. But in an ideal situation with no air resistance, then it means the ball will keep up that motion of bouncing no matter how little till infinity. So it's safe to say that the ball stops bouncing when it's at infinity. So that is a very key concept to know in order to solve this question. So now let's take a more in-depth look at it to get the time at which this occurs. So the total time taken for a single to and fro motion, okay, let me write that down. Time taken for a single to and fro motion of the ball This can be obtained by setting S to be equal to zero. Now, what's the logic behind this? The only time S is equal to zero, that is the vertical height, is when the ball is either at the beginning of the motion or when the ball is just concluding its motion, when it just hits the ground. So, if we set S is equal to zero in the function that we've been given, S is equal to bt minus 16t squared. On setting x is equal to 0, 0 is equal to bt minus 16t squared. Factorizing t, we have t is into bracket b minus 16t. And on solving this, we have t is equal to 0 or t is equal to b divided by 16. So we have two times, which means at t is equal to 0, that's at the beginning of the motion. Then at the end of the motion, b over 16 is the time. So it means time taken for a complete motion, of the ball is equal to b over 16 seconds. Since that has been established, let the initial velocity of the first bounce be b1, which is equal to b. So for the second bounce, let this be equal to b2. So it means for the second bounce, the vertical distance traveled is, remember that the maximum height is b divided by 64, where b is the initial velocity. So in this case, for the second bounce, the vertical distance traveled will be equal to b2 squared divided by 64. We have already been told that the vertical distance traveled for the second bounce is half of that of the first bounce. So b2 squared divided by 64 is 1 over 2 multiplied by b1 squared divided by 64. That means, on simplification, b2 is equal to b1 divided by root 2. That's the relationship between the initial velocities b1 and b2 on the first and second bounce respectively. So it means if we take a look at this, we've established that the ball is going to stop at some point in infinity. So to get the time, we need to have the sum total of the time for each of the bounces till it gets to infinity. So the time taken for the ball to complete the first bounce is B1 divided by 16. Let's write this as total time taken for the ball to stop. So B1 over 16 plus on the second motion becomes B2 divided by 16, B3 divided by 16, B4 divided by 16, and this goes on like that. So we can write all these in terms of B. Remember that B1 is the same thing as B, so B2 is B1 divided by root 2. So B divided by 16, which is B1 over 16, plus B divided by 16 root 2. Plus, remember that we can write the same expression for B3 and B2, which means B3 is the same thing as B2 divided by root 2. So that means we have an extra root 2 term there, which is now B divided by 16 multiplied by root 2 all squared plus B divided by 16 multiplied by root 2 raised to the power of 3, and it goes on like that. So we can factorize this to be B divided by root 16 multiplied by 1 divided by root 2 plus 1 divided by root 2 squared plus 1 divided by root 2 raised to the power of 3 plus the rest of the terms. So within the parentheses, we can see that this is a geometric series with a common ratio of 1 divided by root 2. And since the common ratio is less than 1, we can find the sum to infinity of this, so we can get the value of the time at infinity where the ball stops. So on finding the sum to infinity, we have this to be B divided by root 16. Oh, sorry, there's a 1 missing here, because when we factorize B over 16 out, there should be a 1 there. So this becomes 1 plus this. So B over 16 into brackets, the formula for the sum to infinity of a geometric series is A over 1 minus R, where A is the first term and R is the common ratio. In this case, the first term is 1 divided by 1 minus 1 divided by root 2. So if you go ahead to simplify this, you have B over 16 multiplied by 1 divided by root 2 minus 1 divided by root 2. And this is equal to B over 16 multiplied by root 2 divided by root 2 minus 1. So the time taken for the ball to stop is equal to root 2 divided by root 2 minus 1 multiplied by or times the time taken for the first bounce. If we know the time taken for the first bounce, we can get the time that is going to take for the ball to stop by multiplying it by root 2 divided by root 2 minus 1. When you evaluate that in a calculator, you get something around 3.4. So 3.4 times, roughly 3.4 multiplied by the time taken for the initial bounce or the very first bounce is going to give us the time taken for the ball to stop. With this, we've come to the end of this video on rectilinear motion. I hope you guys enjoy this, and I look forward to seeing you guys in the next video, where we'll be talking about problems on maximum and minimum values of functions.